This is FE Peer Review. The date is February the 20th, 2024. Bev Tries Thinking, about 8 inches per mile squared. My thanks to Blue Marble Science for a video he just put out in which he shares with us a bit of video from Bev Try Thinking, where Bev is pondering the equation of drop being 8 inches per mile squared and what that means. Seems to have a little bit of a struggle with it, and we are going to listen to a little bit of Bev's struggle from Blue Marble's video here. I borrowed this from Blue Marble, and my thanks to him, and you'll find a link to his video in the description. So here goes, over to Bev.
Okay, so we're back to the half mile. Well, if you add those two together, you end up with 4 inches. But if you start from one point and go the whole mile, you have 8 inches. So that's a good point, whoever said that. I think it might have been me.
Uh-oh. Bev's trying to pull into the lead here. He said something incredibly stupid, and he's so proud of it, I'll bet he plays it again.
Right, so here we go. We've got from A to B to C. 2 inches over a half mile. So 2 inches over the first half mile. And that's the same for either of these, right? He should have left that one in there. Well, if you add those two, see, another 2 for the other half mile. Together, you end up with 4 inches. 4 inches, yeah. Now, this one here, from A to B, should stay there, because that doesn't change. That stays at 2, right? Because it's still a half distance for the full thing. But if you start from one, see that 8 inches, 1 point and go the whole mile, you have 8 inches. 8 inches. So there's a difference of 4 inches, isn't there? A difference of 4 inches, isn't there? Between 4 and 8.
That would be a difference of 4. Yep.
He's right there, right? Now, did Petey do that maths right, or did I do that maths right? Does 2 2s add up to 4? And, yeah. 4 isn't 8. And this is what I was pointing out. This is literally what I was pointing out. That you know, there's a difference of 4. Now, how did that happen? Where did it come from? Who knows?
Thank you, Bev. Now we're going to take a look at a couple of little diagrams that I hope will clarify some of the confusion I hear there. For a start, I want to reiterate a couple of points. First of all, the equation 8 inches per mile squared is an approximation, useful over short distances. And by short distances, I mean basically distances that you can look with your naked eye. So standing out on the beach, looking out over the ocean, you're looking several miles. Go up on a high hilltop overlooking the ocean, you can see many more miles. That kind of a distance. I'm not talking about thousands of miles. So it's an approximation, but for most purposes, it works fine over those kinds of distances. Second, I want to clarify, each measurement is taken with reference to a horizontal plane at the observer's location. And I have a typo there, which I'm just going to go ahead and fix. Singular location. Each measurement is taken with reference to a horizontal plane at the observer's location. And I'm going to clarify with another picture exactly what I mean by a horizontal plane at the observer's location. Okay, we have a sphere. We're looking at a sphere here. And I have drawn a plane. And I've made that plane tangent to the sphere at one point. So you can see that they just touch. And what that means is that there is 1 point on this sphere and only 1 point, which is shared by this plane here above it. That's what makes this plane tangent to this sphere. And that point is where our observer is standing. And this plane is the horizontal plane that we're talking about when we're measuring drop. Now, we're accustomed to thinking of north as up and south as down. And from the way I've made this model, we would be imagining that this is a person standing at the North Pole. But it doesn't have to be a person standing at the North Pole. So I'm going to fiddle with this a little bit. So now we're looking at the same sphere, the same plane, but it's somebody standing at some northern latitude up here. And that is their reference horizontal plane. To them, that's the plane that is horizontal at their location. So I hope that makes it clear what we mean by horizontal plane. Now back to our other diagram. Let's start with this one at the top here. We have, look at the heavy line, the heavy solid line that's sloping down to the right. That is a smooth, even, consistent downward slope. It's a straight line sloping down. You can imagine you might be standing at point A, for example, on the left here, and it's a road, and it's a very nicely graded, smooth road that slopes down, going down a hillside. You might see roads like this. You might see railroad tracks that are on smooth grades like this. They like to do that with trains. Also, for example, a wheelchair access ramp could have a very even, consistent downward slope like that. So you're standing at A, and you're looking towards point B, and you decide you want to know how much it's dropping from your point A. So your horizontal reference plane is this dotted line here where I'm moving my mouse between A and B. And you measure out 16 feet. There's 16 feet. You measure out 16 feet, and you measure a vertical, a plumb line from that point straight down to the ground, and that drop is 1 foot. And then you decide to repeat that process, starting at point B and going towards point C. Again, 16 feet, and again you measure a 1 foot drop. And you do that a third time just for good measure. Starting from C, you go towards D, 16 feet, and again you measure a 1 foot drop. Now let's say you want to double check all that and try it again. Starting at A, you want to measure all the way to D and get the drop. So from A, you measure all the way to D, and you get 48 feet, exactly the sum of the 3 previous horizontal measurements that you made. And when you look at the drop, you get exactly 3 foot drop, which is the sum of the 3 drops you measured earlier. So that, Bev, is one of the things you described, and I think what you might have been expecting for Earth curvature drop. Well, it's not Earth curvature drop, but it does work on a straight, smooth ramp like that. Now let's look at what happens when you're measuring drop on a sphere. Here we see a portion of a circle, portion of a sphere. And again, we've got A, B, C, and D. And again, we'll start at A, and we will measure along a horizontal plane from our point A out a certain distance. And we measure 16 feet, and we measure a drop of 1 foot, just like we did before. Just like we did before, that one there. Now we go over to point B, and we repeat that process, but this is where things change. The horizontal plane at point B is the plane that's tangent to the sphere at point B. That's not the same as the tangent at point A because we've curved. So the tangent to point B is this line going from B over towards C, where I'm moving my mouse. That is the tangent to B. We measure along that line, and again we get 16 feet. And then we measure our drop, and again we get 1 foot. And now we're going to repeat that one more time, starting at C. And again, our new horizontal is the tangent at C, coming out towards D. And again, we measure a 1 foot drop. So we've measured 3 1 foot drops and 3 16 foot distances. But if you'll notice the way I've shown these dimension lines, it's a kind of a clue as to what's going on. You see that the first 16-foot measurement from A to B is not parallel with the next 16-foot measurement and is not parallel with the third measurement. The same goes for the drop dimensions. The first drop dimension at B is not the same as at C, where C is starting to lean towards the right, and D leans even more towards the right. So you can see that something's happening there with these measurements. Well, what happens if we measure from A all the way out to D and get the drop? We're going to look at that, and then we'll look at it in stages. Okay, so here goes. From A to B, we get 16 feet. We measure a 1-foot drop. Now I'm going to measure from A to C. A to C. We don't get twice what we measured before. We get slightly less than twice. Twice would be 32 feet. We're 1.5 inches short. Now let's measure horizontally from A all the way out to D. Again, we don't get 3 times our initial measurement. That would be 48 feet. Instead, we get a little less than 48 feet. Now let's look at the drops. Measuring from A to B, we get a 1-foot drop. Measuring from A to C, our drop is now 3 feet 11 5/8 inches, so almost 4 times what we measured at B. And if we do that again from A all the way out to D, we get 8 feet 10.5 inches. That's almost 9 times. So you can see that these don't just add up to match the last one. Same goes with the horizontal dimensions. They don't just add up to match the last one. When you're looking at a curve, because your tangent is not parallel at B and C to your initial location, they're dropping and dropping. The total drop is more than just the little bits in between. You have to account also for that change in the tangent. So that's why, Bev, when you did a 1/2 mile and got a 2-inch drop, and then you did a mile and got an 8-inch drop instead of a 4-inch drop, that's why, because the farther out you go, the faster that curve is dropping away. I want to back up now, just briefly talk about the approximation part of our story here. If you remember, Bev, when you looked at the 1/2 mile distance, you dropped 2 inches. And then when you went to a full mile, you dropped 8 inches. So you dropped 4 times as much. Well, when we look at this example here on the screen, we see that we go out 16 feet, we drop 1 inch. We go out almost 32 feet. And we go down almost 4 feet, but not quite 4 feet. So this is not quite 4 feet because we are dealing with an equation that's an approximation. If we were using our approximation equation, we would have gotten 4 feet, which would have been 3/8 of an inch off. Now, as I said earlier, when you're talking about short distances on Earth, we can use that approximation equation and it works fine for most purposes. But short distances on Earth, what I've drawn here, this much curve, this curved line, that would be hundreds, I don't know, maybe 1,000 miles. I didn't bother to check that, but we're talking about what would be on Earth a very large distance, not a short distance. So if we were measuring something that a distance long enough on Earth that the curvature should be that much, we would definitely start to see a real divergence from our 8 inches per mile squared formula. So the 8 inches per mile squared has its limits, and basically in this diagram here, we've gone past those limits, which is why these figures are pretty substantial. This should be 4 feet, and this should be 9 feet based on 8 inches per mile squared. But when you do the real geometry with a sphere, you'll see that these are more accurate. I hope that helps a little bit. Look at the diagrams for a while, and hopefully that'll make it more clear. Now, keep in mind these distances and I haven't used Earth radius and miles and inches and all that just because it would be pretty much impossible to draw in SketchUp. SketchUp is not designed for drawing things that are many, many miles in size. But the geometry, the geometric principles behind it are exactly the same. Thanks again, Blue Marble Science, and I hope you all find this video mildly interesting at least. If you did, remember there is a like button down there and also a subscribe button if you haven't already subscribed. Bev, if you're watching this and you have any questions, you're welcome to leave a comment as well. I'll do my best to answer them. Have a great day, everybody. Bye-bye.